Hello, Integrated Math 3 and Integrated Math 3 Plus. Welcome to Lesson 12-2. Remember, we were talking about exponential functions, and we were talking about fire ants. We were actually a little worried about Red and his fire ants. I'm still a little concerned about the guy and what he's going to do with them. But remember, we came up with this lovely function to model our fire ant population, 20 times 2 to the x power. And this is actually a transformation of the parent function y equals 2 to the x power. So down here, I have my scatter plot, and you have this also on question number 7 on student activity sheet number 2. But you'll see here I've got my scatter plot of my fire ants, which we did earlier. I don't know why we went to blue. We were using red earlier. I don't know what's going on. But right next to it, I also have my y equals 2 to the x power. And I picked a couple points that match with these x coordinates. So we already discovered last time that when x is 0, we had 20 fire ants. After 1 week, we had 40. 2 weeks, we had 80. 3 weeks, we had 160. And after 4 weeks, we had 320 fire ants. And it has a 2 to the x, just like our little guy here has a 2 to the x power. We know that constant multiplier is what gives us that exponential function with our x in the exponent. Probably why it's called an exponential function. Crazy, right? But here I have y equals 2 to the x power. And that means that at 0, I get an answer of 1. At 1, after 1 week, I get an answer of 2. 2, I get an answer of 4, which makes sense. 2 squared is 4. If I plug in a 3, 2 to the third power is 8. If I plug in a 4, 2 to the fourth power is 16. So how did we get from here to here? I would like you to complete the table. You have a little column in your table that says stretch factor. I would like you to play with this and try to figure out how we got from here to here. Why it is that our scatter plot of the fire ants is so much steeper than our y equals 2 to the x power. So go ahead and hit pause to fill in that table and then hit play when you're ready to check your work. So I noticed that this was a 1 and that's a 20, so I have to multiply by 20 in order to get there. And then I noticed that in order to get from 2 to 40, I also need to multiply that by 20. And if I need 4 to become 80, I need to multiply that by 20. And if I need 8 to become 160, multiply by 20, you get the idea. 16 times 20 would give you 320. So it looks like that 20 out in front of our 2 to the x power is actually stretching our exponential function. Each point of data in the fire ant population is 20 times the value of y equals 2 to the x. So we're going to say, hey, it has a vertical stretch of a factor of 20 or a stretch factor of 20. Because for every point here, every y coordinate here, I had to multiply it by 20 in order to get the y coordinate on y equals 20 times 2 to the x power. So this tells us, I'm going to come to the next page here, this tells us that it's actually a pretty good model for our fire ant population. That we've got that 2 to the x exponential going on, but we're multiplying by 20 every time. But if you come over to question 8, let's start looking at some of these other things here. So question 8 on student activity sheet 1, and actually real quick before we do that, here is our 2 to the x, and sure enough, if I stretch it by a factor of 20, remember we use an a value for that, so if I stretch it by a factor of 20, if I turn my a into 20, oh, look at that. It matches our fire ant population perfectly. So here's the deal if we're looking at questions 8, 9, and 10. We're going to play with these a little bit. An exponential function can be written as f of x equals a times b to the x. And of course, b is the base. And we're going to point out that b needs to be greater than 0. And there are some textbooks that will also say that your base, your b, can't be 1. And that base b is the constant multiplier found in the data. Times 2 times 2 times 2 means that 2 is going to be the base of my exponential function, 2 to the x power. So the variable a, that's our parameter that modifies our b to the x. And we notice that a is going to stretch or compress the values of our function y equals b to the x. I think that actually answers for you questions 8 and 9, what kind of restrictions you've got on B, and also the value, what the value of A represents on our general function. So make notes of that on questions 8 and 9. And then I also want you to answer question 10. What is the value of f of x equals a times b to the x when x is 0? Go ahead and hit pause and give that some thought, and then hit play when you're ready to check your work. So if I plug in a 0, and you need to remember that we always do exponents before we multiply, b to the 0 power. Well, guys, anything to the 0 power is 1, right? So b to the 0 power is 1. So if I plug in a b to the 0 power is 1. So I'm actually just doing a times 1. So that means f of 0 is a. If I plug in a 0, I'm always going to get that stretch value, which means while we're used to thinking of a as a stretch factor, here's what it means for exponential functions. It means that that a value out in front, which we know is the stretch factor, vertically stretches it, all that good stuff, it's also the y-intercept of the graph every single time. That a value is your y-intercept, which is, well, kind of freaking awesome. So in the fire ant data, where remember how x equals 0, where we started out before we'd had the ants for any period of time, they started off with 20 fire ants. So sure enough, on the graph, that was the value of a. So sure enough, that means that that a value, that 20 is my y-intercept. And that b value, this b, that base of my exponential, is my constant multiplier. So a is always going to be my stretch factor, also known as my y-intercept, and b is always going to be my constant multiplier. So that actually makes it kind of convenient to figure out some of these lovely little guys. We're going to skip a few questions here, and we're going to go over to questions 13 and 14. So what do you think the value of b in the general exponential function, why do you think that value is restricted to values of b greater than 0? So take a few moments. What happens if b equals 0 on your general exponential function, right? Because we said it had to be greater than 0. We're like, it has to be greater than 0. So what do you think happens if b equals 0? Go ahead and hit pause to give that some thought. And then once you've done that one, think about what happens if b is a negative value. So go ahead and hit pause to give this some thought, and then hit play when you're ready to check your work. So if b is 0, I have a problem, right? Because 0 to whatever power is going to be 0, and that's going to kill off anything else I'm trying to do. So if b is 0, then I have a function of a times 0 to the x power, and I don't care what positive value x is, x whatever is going to be 0. Now, of course, there are some issues because if x equals 0, 0 to the 0 power actually doesn't exist. Because anything to the 0 power is 1, but 0 raised to any power is 0. So this doesn't even exist. It creates all kinds of problems for us. So here's the deal. If b were equal to 0, I wouldn't have an exponential function. There would just be a horizontal line at y equals 0, and then there'd be some problems when I tried to plug in a 0. So this just doesn't work for us. It's just not going to work for us. And the other question that was brought up is, what if your base is a negative value? If your base is a negative value, this starts to create some problems. And let me see if I can show you why. You remember that exponential rules, right? So if I have fractional powers, which we are allowed to have, if I said x equals 1/2, and I have b to the 1/2 power, if you remember, 1/2 means a square root. Or if I have the power of 1/4, it's a 4th root. Guys, if b is a negative number, I can't do the square root, and I can't do the 4th root. I can't graph that. They're imaginary. They're not real. So there would be a lot of undefined values since you can't take the root, an even root of a negative number. So typically then, this means for us, this means that B is kind of special. This means that my B, my base of my exponential, has to be greater than 0. We can't have it equal 0 because it would just flatline it. And we can't have it be less than 0 because that would create some undefined moments when I try to do roots, and that's no good. Wow, that's a lot about B. So let's finish this off with questions 15 and 16. Now that we've obsessed over B an awful lot, let's come back to this guy, our y equals 2 to the x power. And I'd like you to take a look at this graph, and I would like to tell me, hey, what's my domain? What's my range? Go ahead and hit pause to work that out, and then hit play when you're ready to check your work. So my domain, well, it goes forever and ever to the right, and it does go forever and ever to the left. It goes forever and ever to the left, and it does go forever and ever to the right. It's just going up like crazy. So this means that my domain is all real numbers. I can plug anything in for x that I want. Positive, negative, fractions, decimals. I can plug in anything I want. My calculator can do it. It can take it. So my domain is all real numbers, but check out my range. It does go up forever and ever. I totally agree. But check out how it flatlines down here at 0. In fact, I don't even know that it ever actually equals 0. It just kind of flatlines out there. So this means that while my domain, and this is a lot of writing, I'm so sorry, my domain is all real numbers, my range is all real numbers greater than 0. And if you wanted to, you could write that in interval notation. Now, I have one more question for you, question number 16. Can we talk about the end behaviors of this function? So let's describe the end behavior of the function for question 16. As x gets really, really big, as I'm moving to the right, as x goes infinitely huge, so as x approaches infinity, check out what my function's doing. It's going up forever. It's also approaching infinity. But my end behavior on the left side is different because as x gets infinitely small, we're heading forever left, we're heading toward negative infinity. And I'm going to close that. I feel like that's a distraction. If I head forever and ever left towards negative infinity, then my function is heading towards 0. It never actually crosses it, though. So I would say as x approaches negative infinity, f of x is approaching 0. As I go forever left, my y value is heading towards 0. And as I move forever right, as x approaches infinity, so forever and ever to the right, my function is going crazy up. So I'm going to say my y value, or f of x, is approaching infinity as well. We're going to play with these a little bit more with our transformations and all that good stuff. In the meantime, I hope you found this helpful. I hope you found this useful. If you got questions or concerns, please feel free to email me or come see me after school Tuesdays and Thursdays. You know I'll be around, and I'll see you soon. Bye.